Welcome to the lecture series in chemistry under the auspices of the National Program on Technology Enhanced Learning. This is a series of lectures in chemistry which we perceive as basic importance to all engineering and chemistry students who begin their academic career. This is a series of lectures on atomic and molecular aspects of chemistry. It's a quantum chemistry of atoms and molecules. We have had several lectures already on the solution of the Schrodinger equation, and also the last lecture and the previous one concentrated on the solutions of the Schrodinger equation for the hydrogen atom. Okay. Today we continue with the solutions for the hydrogen atom, and we continue the pictorial demonstrations, through the animations, two-dimensional and three-dimensional, of certain aspects of the solutions of the Schrodinger equation. Okay. Let me start with the basic slides. Okay, who I am. I am MangalaSunder from the Department of Chemistry, and my email address is given below as mangal@iitm.ac.in. This is the 8th lecture on the model problems in quantum chemistry, and we continue to visualize the angular solutions to the hydrogen atom problem as proposed by the Schrodinger equation and the solution. The content for today's lecture is essentially, the contents are essentially solutions for the angular equation through visualization of the angular functions using both 2D and 3D graphics, and if time permits we will also see the plots of radial functions. What is extremely important in this set of lectures as given for the students is the enabling you to visualize these solutions rather than derive these solutions mathematically. The differential equations are hard. You need a certain amount of special functions mathematics to derive the solutions through the standard procedure. That's not of importance to us from the chemistry standpoint. We want to see how quickly that the atomic orbitals can be visualized and how quickly that we can keep a mental picture that we already started with in the high school days with the pictures of the hydrogen atom orbitals in the textbooks. Okay? So let us see today in the lectures here. Let me recall the angular equation here. You remember from the previous lecture, the angular variables for the hydrogen atom satisfy the differential equation given by the equation here. 1 by sine theta, the partial derivative with respect to theta, sine theta, dou by dou theta. This is the partial derivative of the function y which we are trying to obtain, plus 1 by sine square theta dou square the same function y of dou phi square is equal to a constant times the function y. Y's were introduced to you earlier as spherical harmonics as a function of both theta and phi, and we started looking at some of the functional forms of the spherical harmonics in the last lecture. And you also kindly recall that the solutions to the theta phi equations contain two quantum numbers m and l, where the values of L are determined by the radial equation whose principal quantum number is n, and the value of L is from 0 to n minus 1. For any given value of L, the values of m are known to be between minus L plus 1, minus L plus 2 all the way up to L in integer steps. That is, there are two L plus 1 values of m for each value of L, and these are of course solutions for the angular parts only. They are independent of the radial coordinate r. The mathematical notation is that they are denoted by the spherical harmonics of spherical tensor of rank L and the spherical component m. In the previous lecture we looked at the L equal to 1 case, and we looked at the 2D, 3D, that is two-dimensional and three-dimensional representations of these wave functions on a polar plot. Okay. We will continue that here for the L equal to 2 case. Obviously there are 5 such spherical harmonics, and representing them in a polar coordinate is an exercise that is worth doing for anyone who solves the Schrodinger equation for the first time. Here we are not actually solving the equation, we are giving the solutions of the equation, because the mathematics is hard enough that we can postpone that to a later lecture. But what is important is, of course, to visualize these solutions. So what you see here are the 3 of the 5 spherical harmonics corresponding to L equal to 2. The m value equal to 2 is given by the spherical harmonic y22. Some constants here. I'll show you how we get these constants at either in this or the next lecture. That's not important right now. It is sine square theta exponential 2I phi. That is important. M equal to 2 exponential 2I phi. M corresponds to the variable phi and L corresponds to the variable theta. You see the colors are more or less to indicate that kind of association. Sine square theta e to the 2I phi. L equal to 2, m equal to 1. The spherical harmonic is denoted y21. Again, constants which don't appear all that random. You see this is root 15 by 32 pi minus 2 times that sin theta cos theta e to the I phi. Again, m equal to 1 e to the I1 phi or phi e to the I1 phi. L equal to 2, m equal to 0. You don't have any exponential phi part, but that's the equivalent of e to the I0 times phi. But the angular part, the other angle is 3 cos square theta minus 1. For L equal to 2 and m equal to minus 1, the spherical harmonic is y2 minus 1, root 15 by 8 pi. Go back and look at y21, root 15 by 8 pi, but with a minus sign. M equal to 1 has sin theta cos theta e to the I phi. M equal to minus 1 has sin theta cos theta e to the minus I phi, I phi, which is again the corresponding m value. L equal to 2, m equal to minus 2, sin square theta e to the minus 2 I phi. So these are the 5 spherical harmonic that we want to visualize in a polar plot. The Cartesian plots are something that you are very familiar, x, y, z. I've been telling in the previous lectures what is the difference between a typical Cartesian plot and the polar plot. We try to plot the x, y and z orbitals for the p, that is L equal to 1 case. The L equal to 2 case is known as the d orbitals, and in the atomic spectroscopy parlance it is d is diffuse. You recall sharp is for S, principal is for P, diffuse is for D, and fundamental is for F. These are the 4 spectral series that were discussed by the atomic spectroscopists even before quantum mechanics came into existence. The theory was put forward even before that. Now the L equal to 2 corresponds to the d orbitals, and you know for L equal to 2 the principal quantum number has to be n equal to 3 or more, because the maximum value of L is n minus 1. Therefore L cannot be 2 unless n is 3 or more. So let us take the lowest n value for which L is 2 is an allowed quantity. So 3d orbitals. Let us look at the angular parts of the 3d orbitals. Okay. Then to complete this, the next set is of course the f orbitals corresponding to the L value 3, and for the L equal to 3 case there are 7 spherical harmonics from plus 3 to 1, 0, minus 1, minus 2, minus 3, as you see in this table as well as in the last one. But let me go up and tell you that for m equal to 3 you have sin cube theta e to the 3 I phi, m equal to 2 sin square theta cos theta e to the 2 I phi. So the m's are reflected by the exponents in the exponential of I phi, 2 I phi, 3 I phi, I phi, etc. The number of such sine functions. The degree here is 3, the degree here is 3, the degree here is 3 and 1, 3 is the higher, sine theta cos square theta. So if you look at that degree, 5 cos cube theta, sine theta cos square theta, sine square theta cos theta, all of these correspond to L equal to 3. The trigonometric functions have a degree of 3 and the exponential phi functions have the m as the running index for the corresponding exponential functions. This is a way of, what I would say, identifying a pattern in these wave functions. See, the first thing when you look at mathematics is, all of us would like to derive, if we want to understand, the equations themselves. Now if we cannot derive the equations because of the mathematical skills required or because of the details involved, let's at least quantify these functions by looking at them somewhat closely and see how we identify these patterns. Spherical harmonics give you beautiful patterns. By the way, spherical harmonics is not of interest only to quantum chemistry. Those who study electromagnetics, those who study aeronautics, those who study, I mean, all kinds of engineering comes with the spherical harmonics pattern in every one of them. Therefore, aside from looking at it as orbitals, you can also see these as visualizations of spherical harmonics as applicable to your respective engineering branches. Okay. So now let us look at the visualization part of the 2D and 3D the 3D animations, and the orbitals that we are plotting are the 3D angular functions. But before, let me give you a little bit about the notation. Okay. You must recall that earlier in the last lecture when we wrote a px orbital, we took this as a linear combination of the spherical harmonic y11 and y1 minus 1. This was fairly simple because you looked at this formula, it was e to the I phi sine theta with a minus sign, and this had a minus, of course, sine theta e to the minus I phi, and this linear combination, we needed to take that because this is a complex function, this is also a complex function. We cannot plot the complex functions as they are, but we have to plot the real and the imaginary parts of the complex functions separately, and if you want to do that, you have to actually take the real part of the function, the imaginary part of the function, which means you have to take linear combinations of real and imaginary parts by taking the function and its complex conjugate. You see that y11 and y1 minus 1 are related to each other through complex conjugation, e to the I phi, e to the minus I phi, but with a minus sign in front. Okay? So this gave you the quantity sine theta cos phi, leaving aside all the other things like minus 2, leave that, don't worry about it right now. Sine theta cos phi, and that, you know, in polar coordinates is like x. That's a definition of the spherical polar coordinate representation for x, and for y it is sine theta sine phi, and obviously you got sine theta sine phi from the linear combination sine theta e to the I phi minus sine theta e to the minus I phi, and this gave you basically sine theta sine phi. Okay. Now this was Py orbital, and with respect to Pz there was no problem, it was simply cos theta, which is the spherical harmonic y10, okay, proportional to the spherical harmonic. So the orbital notations as the real and imaginary parts of the spherical harmonic were implied by these labels Px, Py and Pz. Now let us do the same thing for the d orbitals. You have to recall from your elementary chemistry that the 5 d orbitals from textbooks, from your high school textbooks and also any other quantum chemistry book, is that the notations are dx square minus y square, dxy, dxz, dyz, and dz square, but which is typically it is d3z square minus r square. I mean, in order to write this, people usually call this as d square z square, but the correct notation is d3z square minus r square. Now where do these things come from? You have to look at the spherical harmonic closely. Let's go back and look at the functional forms here. Okay. Let's look at L equal to 2, m equal to 2, sine square theta e to the 2 I phi. Okay. Now what is the real part of this function. The real part of this function is sin square theta cos 2 phi. The imaginary part is sin square theta sin 2 phi. Let us look at those. Sin square theta cos 2 phi. Okay. This is the real part of spherical harmonics y22. This is nothing but sin square theta cos square phi minus sin square phi. Okay. And if you recall that this is nothing but sin theta cos phi whole square minus sin theta sin phi whole square. What is this? This is x square minus y square. Therefore, the label dx square minus y square corresponds to the real part of y22 with the L equal to 2. L equal to 2 is for d, the real y22 is for this x square minus y square. Okay. So, you remember that these labels x square, y square, xy, xz, yz, they are not arbitrary. Okay. In fact, you go back further in mathematics, you will find that these spherical harmonics have a certain degree of symmetry and they have a property of what is called the irreducibility under the group representation and all those things anyway. Leave that jargon aside now. That is a mathematical firm basis for the way the spherical harmonics come out as solutions of the Schrodinger part, the angular equation part, and we see that the chemists make absolutely perfect use of these orbitals in describing the chemistry of what goes on. Okay. So let us look at the shape of these orbitals now. What is d x y? Should be obvious now. It is sin theta cos phi is for x and y is sin theta sin phi, and therefore this is nothing but it is sin square theta cos phi sin phi is sin 2 phi. Sin 2 phi is of course the real part of e to the 2I phi, sorry, the imaginary part of e to the 2I phi. I have this little gadget which tells me how to do all these things cleanly. Okay, so there you go. So we can write the imaginary part of e to the 2I phi. Okay, is sin 2 phi, and this is of course what you see is y to 2. This 2 is for the L equal to 2 degree 2 sin square theta. This 2 is for the m equal to 2 for the exponential function. So again the imaginary part of y22 gives you dxy. The real part of y22 gives you dx square minus y square. Therefore there is no more mystery regarding these labels from the table of spherical harmonics. Okay. If I go further in this quickly, I will show you that association. This is the table that you have to remember. In fact, you can construct this right away. 3z square minus r square is cos square theta, 3 cos square theta minus 1. That is what you would get from the y20. This is the form of y20. X square minus y square, I just now explained the sin square theta cos 2 phi. Xy also I explained the sin square theta sin 2 phi. Xz and yz therefore come likewise from sin phi and cos phi. You remember that the sin phi comes from the e to the I phi, I m phi where m is 1. Therefore these two correspond to the spherical harmonic y2 but with the m value plus and minus 1. Real and imaginary parts of y21 are obtained by the linear combinations of these two. Therefore all the 5 spherical harmonic, all the 5 spherical harmonic or harmonics give you these 5 different functions, namely z square minus r square, x square minus y square, xy, xz and yz. Those of you who would study a little bit more of the inorganic chemistry, to study the chemistry of materials and the things that the molecules that the materials are made of, you will realize that these labels are extremely important in the field of what is known as coordination compounds. So these are not trivial labeling, but let us look at the objective, namely the visual representation of these orbitals now one by one. The rest of today's lecture will see all these 5 orbitals or the angular representations closely. Okay. First, dxy orbital. My strategy for this lecture is to first show you what the picture looks like and then go back and build this picture from the elementary plotting parts of the two variable function like we did in the last lecture, so that you see that the picture that you saw is not something that is arbitrary but is built up from very solid mathematical plotting. Okay. Let us look at the dxy orbital first. Okay. Dxy orbital corresponds to two pairs of lobes with two different colors. You see the green and the blue here. Okay. Pairs of lobes pointing along the diagonals of the xy axis system. You see that they are not, they are in the xy plane, they also of course come out of the xy plane, but they are pointing along the diagonals of the xy plane. What about the next one? This is dxy, the dyz. You shouldn't expect anything stranger. You should expect that it is pointing now along the yz plane but along the diagonals of the yz plane. As you see here, see, dyz is pointing the two lobes here and the other two lobes, the green lobes, they are both pointing along the diagonals. Let us look at the dyz orbital. Sorry, that is what we did. So let us look at the dxz orbital. Again you get the picture that the lobes are pointing along the xz plane but along the diagonals in that plane, not along the axis themselves. Okay. Next one, dx square minus y square orbital. You see, now that looks exactly like the dxy, except that now the orbitals point along the axis, the lobes point along the axis here, the plus and the minus axis. The last one in this, the fifth one, is the d3z square minus r square orbital, which looks like having a lobe, two pair of lobes pointing along the z and the minus z and a ring surrounding. This ring is obviously symmetric in the xy plane, so you see that there is something which appears somewhat different from the other four sets. Now these are the final pictures. These kind of animations you can find anywhere, but what you will not find is the method of building these animations by looking at the function and then plotting them in the polar graph. That is the step that we will follow next. So let us look at the y22, which is cos 2 phi sin square theta. First we will plot this for one value of phi, and then we will sin square theta for all the values of theta, and then we will extrapolate that plot to all the values of phi, just as we do in a three-dimensional plot. So let us look at the flash file for this particular function. Okay. So what I have here is sin square theta cos 2 phi. Now recall the definition of the theta and the phi. The theta is obviously along the z to minus z, it is a polar axis. You remember the pictures we had earlier. The variation is theta is equal to 0 here, slightly one value and so on, and obviously 90 degrees, and then when you go to minus z it becomes 180 degrees. The phi is for a given value of theta, of course anywhere. If you go across the sphere through a circular path, that is the value of phi, going from the x-axis as phi is equal to 0 to y-axis phi is equal to 90, minus 180 degrees is for the minus x-axis, 270 for the minus y, and then back to 360 degrees and 0 degrees for the x-axis. So we now plot this for one value of cos phi, namely phi equal to 0, which means we are plotting this function along the x-axis, this. And the value theta is sin square theta, the functions are given here. You know, theta is given from 0 to 180, sin square theta is given from 0 to whatever is the corresponding value, and the plot is for any value of theta, the magnitude sin square theta is plotted along the radius, as you have done in the previous Px, Py, Pz graphs in the last lecture. 15, 30 degrees it is 1 by 4, 45 degrees is 1 by 2 and so on. So you see the values of whatever is the theta and sine square theta are plotted. Okay. You know what is the value of theta if you go back to this graph. See what is the value? This represents the theta is this angle, the theta is 75 degrees and the corresponding value 0.933 is 0.933 in a circle of radius 1. You can mark that, you saw that, that is how you plotted it. You see this 0.93 is the value in a circle of radius 1 and that of course cuts this radius here, so this value is also 0.93. So there should not be any doubt about how this plot comes about. Okay. So let me complete this particular plot. Okay, so this is sine square theta. It is not spherical as it is in the case of sine theta, but it is some sort of a slightly distorted shape. Now this is for one value of phi, namely phi equal to 0, cos 2 phi is 1 at phi equal to 0. This, if we plot the same function, same graph for every value of phi by multiplying that with cos 2 phi, we get the 3-dimensional representation of the function sine square theta cos 2 phi. That is the next plot in the 3D file. So here you have it along the x-axis and then this is now plotted along all the possible values of phi by taking a few samples and then connecting all of them together, and that is multiplying all at the same time with cos 2 phi. Okay, so that is the way the function looks like. Just go back and see what it means. Okay. The nice thing about all these animations is that you can play back and forth and learn at your own pace. Okay, now I have stopped at a point roughly where phi is 45 degrees. Okay, maybe yeah, this is 45 degrees. I mean at 45 degrees phi value cos 2 phi is 0, so you see that this function has disappeared completely. And at angles greater than 45 cos 2 phi is negative, but it keeps building up, cos 90, cos phi equal to 90 means cos pi which is minus 1, that is the highest value in the negative side. So you see that the value again builds up and it becomes most negative along the y-axis. Okay. That is what you see, it becomes exactly like what it was along the x-axis, except that the function on this side is negative because of cos 2 phi. Sine square theta is always positive, no problems. Now as you go further, cos 2 phi goes from 180 degrees to 270 degrees as phi goes from 90 to 135, and you see that it again goes to 0. Okay. So this whole part is negative, this part is positive, and you continue this process until you go through the rest and you see that the positive and negative parts alternate, leading to the two different colors of the function, and this is typically what you write in your high school plots for the d orbital xyz, xy and yz and zx. You put two minuses on one pair of lobes and you put two pluses on the other pair. What do they mean? They represent nothing but the signs of the function, the actual value of the function with its magnitude and the signs. So that is what you see here. So this is a dx square minus y square, and it points along the lobes, and this is in agreement with the picture that we had earlier. Okay. Next one, the imaginary part of y22 is sine 2 phi sine 2 square theta. See, the theta part is still sine square theta, but the phi part is sine 2 phi. So if you look at the flash file, the only thing that we have to do now is we should not plot this for phi equal to 0, because for phi equal to 0 the value is 0, sin square theta sin 2 phi is 0. Therefore, if we want to plot a particular value of phi, keep the value and change the sin square theta for various values of theta, the most convenient point is phi equal to 45 degrees, okay, not phi equal to 0. So if it is phi is 45, obviously you see that the x and y axis, if you represent them, somewhere from the middle that this function starts its value, and the final plot is a sin square theta plot, which is the same as the previous plot. So let me just draw the final plot, okay. The last frame is obviously along 45 degrees sin square theta with cos sin 2 phi is equal to 1 at phi equal to 45. Now this plot gets obviously repeated by sin 2 phi modulation in the 3-dimensional picture. Okay. So when we go to the 3D part of the imaginary part of y22, okay, everything is the same as the previous one, except that now the maximum lies along 45 degrees, not along the x axis, because at the x axis sin 2 phi is 0. So all that seems to happen is that the previous plot which you saw as between x and y, seems to have been tilted by about 45 degrees because of the value sin 2 phi, and that is exactly what is reflected in this picture of the imaginary part of the y22. Well, it is very easy to remember if you remember that sine function and cosine function are essentially different from each other by a phase angle of 90 degrees. Okay. This is sine 2 theta, therefore the phase angle here is 45 instead of 90 degrees. So what you have here is dxy, which is the orbital pointing between the axis with the maxima between the axis and along the diagonals, and again with 2 positive parts and 2 negative parts. The yellows are positive, the slightly brown or grayish ones are negative. This is for y22 imaginary part, or what we call as the dxy. Now there should not be any more surprises regarding what should be the imaginary part, real part of the y21 and y2 minus 1. They correspond from this function, as you see, cos phi sin 2 theta. Cos phi sin 2 theta is cos phi cos theta sin theta. Sin theta cos phi is x cos theta, so this is xz orbital. Plotting this, we are going to plot this for phi equal to 0 because it is a cos phi, and sin theta cos theta plot has something slightly different from the previous plot, so it is worth going through the plotting routine again. The values are given here and the points are plotted along the radii, making the angle theta. So let me stop at the halfway point. The reason for the halfway point break is sin theta cos theta. Obviously it goes to 0 when theta is equal to 90 degrees. So you see that the function starts from 0 and it goes through some maximum and then it comes back to 0, and throughout this part the function remained positive. But now as theta increases, sin theta cos theta is going to be negative. Again it goes through the same, except that now it is along the bottom part of the axis system. Okay, let's play that now. And what you see here is the mirror image of that plot, except that the values are all negative, not by saying this is the negative, no, there is nothing called the negative here, the function is negative. This axis does not make any meaning right now, this axis is only to reference 0 angle and 180 degree angle. Z axis is 0, the angle theta is equal to 0 is here, the angle theta is equal to 180 is here, that is the only reference. You can't mark along the axis anything. This is not a Cartesian plot, this is a polar plot. So only the radius and the length along the radius that are important. So now you see sin theta cos theta has this positive and the negative lobe, the red is positive, the blue is negative, and this has to be plotted as a function of cos phi for all values of phi, which is given in the 3-dimensional file. As you see, slightly more expanded version, sin theta cos theta here along the x axis, and then you plot this. It is modulated by cos phi, so it goes to 0 at phi equal to 90, goes to -1 at phi equal to 180. You see that the lobes are pointing in the xz plane and there is nothing along the y plane, because at y the value is 90 and therefore cos phi is 0. So you see that these lobes are identical to the xy lobes, except that now they are in the xz plane. And let me do one more plot here on the y20, namely 3 cos square theta minus 1. That's a slightly interesting plot. There is no phi dependence for this function, and 3 cos square theta minus 1, when you calculate for various values of theta, the table is here, for theta is equal to 0, 3 cos square theta minus 1 is 2, and there is a value of theta for which this goes to 0, which is cos theta is equal to 1 by root 3. 1 by root 3 cos theta is theta is equal to 54.74 degrees. Also theta is equal to pi minus 54.74 degrees, both of them, for which this function goes to 0. Okay, this is a 0, there is a 0 here, and in between the 3 cos square theta is less than 1, therefore the function takes a negative sign between these two zeros, otherwise the function is positive. Let us see what the plot looks like. Okay, the function is already 0 at this point, okay, that is theta is equal to, this angle theta is 54 degrees, 54.74, and the function up to now is positive, but now it becomes negative, it increases and then goes back to 0 again. So let me complete this plot. The rest of this part is identical to what you have on the top. So the function looks like, see the plot, when you connect all these points, the function goes to 0, then there is a negative part, then there is again a positive part, and this is independent of phi. Therefore when you plot this in the 3-dimensional axis system, 3 cos square theta minus 1 in the spherical polar representation, you get the picture that we saw in the beginning, namely the lobes with a ring in the middle. It's phi independent, so it's the same plot, and you simply repeat that for all the values of phi. So you get two lobes and a ring in between, and the ring is negative, the lobes are positive. Now having done this, if you go back and look at the 3z square minus r square orbital, you see that this was a slightly different colored representation, but you see that two lobes and a ring in between gave you how to build these functions from scratch once you know how to plot them in the polar graphs. All of the angular, the orbitals that you see as pictorial representations in textbooks, in quantum mechanics textbooks and any physical chemistry textbooks, which are called the orbitals, they are not exactly orbitals. What you see are basically the angular functions, the real and imaginary parts of the angular function being plotted on the polar graph. This gives you, for a given radius, given r value, how is the wave function distributed along a sphere. And the spherical coordinate system is the fundamentally useful coordinate system for hydrogen atom, because the electron nucleus interaction is the same for any given distance irrespective of where that axis is or where on the sphere of radius that the electron is moving around. See, but that is a classical picture. That is, one assumes the electron to be like a dot moving around a sphere having an interaction with the nucleus. Now that picture does not have any meaning the moment you associate a wave function with the electron through the solution of the Schrodinger equation. All that you have is that a function which itself is not a very meaningful function, because wave function does not have an interpretation in quantum mechanics. I have been telling you this several times. It is the absolute square of the wave function calculated in a very small region of space that is related to the probability that the wave function, that the system is in that region. That is the only interpretation for this. So what is the meaning of all these plots, and why should we go through representing functions so elaborately and so carefully when we know that in the end these functions themselves are a meaningless quantity? The reason is, when you do quantum chemistry, when you want to see how the atoms react to form molecules, and the atomic orbitals are interpreted as combining to give molecular orbitals, the linear combination of the atomic orbitals, which is a procedure by which we understand chemical bonding, requires us to understand the functional forms of these orbitals very clearly. One has to understand how a p orbital looks like. One has to know how a d orbital looks like from one atom and another atom, and when the two come together, what kind of an overlap between these orbitals takes place. Chemical bonding is interpreted as nothing but the overlaps of the atomic orbital, constructive overlaps. If the overlaps are destructive, we do not call them chemical bonding, but we call them chemical anti-bonding. Okay? See, the interpretation of the molecular nature and the associations of atoms to form molecules goes back to the use of these wave functions based on the hydrogen atom atomic orbitals. A carbon atom nucleus of course does not have the atomic orbitals like that of a hydrogen atom. In the case of hydrogen atom, there is only one electron. When you go to carbon atom, you have got 6 electrons, there is the electron-electron repulsion, but then there are theories which build on these approximations and treat the atomic orbitals as a useful, fundamentally important quantities from which you build the atomic orbitals of the other atoms, and from which you also build the molecular orbitals of various molecules. And in that sense, an understanding, a visualization, a mental pictorial representation of the hydrogen atom orbitals are extremely important, even though the functions themselves do not have an interpretation, do not have a physical interpretation. Okay? Well, we have to keep this in mind when we go through the mathematics of all these things without deriving the mathematics. See, we are treading on very, very carefully on waters whose depth we do not know, but we want to understand how the surface looks like. Okay? Let me summarize this part of the angular function, and let me go back to the plots of the radial functions in a few minutes. Let us examine now the radial part of the hydrogen atom solutions. The radial functions, when we discussed the solutions for the radial part, the radial functions were described for n as a principal quantum number. For n equal to 1, there was one radial function. Now you recall the lesson about 1.5 hours before this lecture. For n equal to 1, there was one radial function, and for n equal to 2, there were two radial functions, namely with the quantum number L equal to 0 and L equal to 1. The quantum number L equal to 0 we have represented as the s orbital or spherical, but it is ideally it is the label sharp. Okay. L equal to 1 also was a radial function for n equal to 2. When the principal quantum number is the next number, n is 3, there were 3 radial functions and so on. So let us look at the functional forms of the radial function with the justification for the radial functions and the wave functions I gave a few minutes ago. Okay. The first one corresponding to n equal to 1 and L equal to 0 is a constant, and let me read this out. It is exponential of minus z or by a naught. Okay. Let me write that. The n equal to 1, L equal to 0, the radial function is r n L r. This is the notation, and that is r 1 0 of r is, leaving the constants out, it is exponential minus z r by a naught. Z is the charge on the hydrogen atom nucleus, which is plus 1, and a naught is the Bohr radius. A naught has a constant value of 0.53 angstroms, okay, also known as the Bohr radius, in honor of Niels Bohr, whose discovery on the hydrogen atom was one of the most important developments in the history of physics. Okay. Now if you look at this form, e to the minus z r by a naught, obviously r by a naught is dimensionless, it has to be dimensionless, otherwise the exponential quantities do not make sense. So what you have is the function, radial function, decreases with respect to r like the exponential. This is what you see in the plot here. It is an e to the minus r by a naught. You see the function has a maximum value, there is a constant in front of it, therefore that takes the value, and then it is a simple exponential decaying as r goes down, goes to very large values, and you see that even though that the r value in principle can take anywhere from 0 to infinity, that is the radius of the sphere can be 0 to infinity, you see that this function drops by 4 atomic units, 5 atomic units here, 4 to 5 atomic units, the function becomes negligibly small. Anyway, it never reaches 0 until r goes to infinity, but it's practically 0. For all practical purposes it is 0. So it doesn't mean that even though with respect to a hydrogen atom the electron has infinitely large dimensional degree of freedom, that is the radius can be 0 to infinity, but now you are in Madras, the electron coordinate is in Los Angeles, there is no way we can call this the electron belonging to the hydrogen atom in Chennai. Okay, it doesn't make sense. Okay. Within 3 to 4 atomic units the wave functions are becoming more or less unimportant for this idea, this mathematical limit to exist only as a mathematical limit, but with no real physical reasoning. So the value r is restricted for the n equal to 1, L equal to 0 case to just about 2 to 3 atomic radii. What is the next one? The next function for n equal to 2 and L equal to 0, let me write this out. For n equal to 2, L equal to 0, the radial function is r2 0 or n L of r is roughly 1 minus z r by 2 a naught e to the minus z r by 2 a naught. Don't worry about how we derive these things. This derivation comes from the solution of the Laguerre polynomial equation, which we did not solve. We are only looking at the final solutions and trying to make sense out of it. So again there is a dimensionless number here, and then e to the minus z r by 2 a naught. Okay. In principle r n L of r will have an exponential of minus z r by n a naught. Okay, so this n is indicative of what quantum number, what atomic orbital that we are talking about. N equal to 1 corresponds to the what is this, the shell K, L, M, N shells, I don't know, you might remember this, the K shell, the L shell, the M shell and the N shell for the hydrogen atom, those are determined by the values of N. Okay. So minus z r by n a naught tells you what shell you are in. Now R20 looks like 1 minus ZR by 2A0 e to the minus ZR by 2A0. What does it look like functionally? When you plot them in a graph, the function has a graphical representation like this. At r equal to 0, this is 0, it's 1, and this exponential is 1, it's maximum. And for as r increases, for an intermediate value of r, this function decreases, but this is dominant in the beginning, so it goes down. And at the value r equal to a0, zr by 2a0 equal to 1, this function goes to 0. This is called a radial node. Okay. Then for all the other values of r greater than this value, this is negative. Therefore, the function is negative all along, and eventually the exponential decrease is much more than the increase here, so the exponential eventually brings it to 0, okay, from the most negative value to 0. So you see that there is a very, what is called a minimum when there is a node, and this function has this feature. Okay. The second radial function associated with the n equal to 2 is the L equal to 1 case. The n equal to 2, L equal to 1 case, the functional form is some constants zr by a0 e to the minus zr by 2a0. The functional form is R21 or zr by a0, okay, e to the minus zr by 2a0. Okay. Obviously, for r equal to 0, this goes to 0, okay, and as r increases, this keeps on increasing. It is always positive, but this keeps decreasing. So there is a tug of war between the increase due to this r and the decrease due to the exponential. And you see the graph. The graphical representation is that there is a maximum and then it goes to 0. Okay. Nowhere does it become 0 for any value of r in between 0 and infinity. Okay. There is no value, there is no node in between. N equal to 3, the radial function is somewhat complicated. Now, one of the reasons why I didn't want to derive all these polynomials is that the mathematics is a separate course by itself. The algebraic results, how do we interpret them, is important. N equal to 3, L equal to 0 corresponds to an exponential which may not be visible here, but it is exponential minus zr by 3a0. And then there is a quadratic equation in front here. 3 minus 6 zr by 3a0 plus 2 zr square by 3a0. So there is an r square, r as a constant. Okay. So let me write that here in the generic form. R30 is some constant a plus b r plus c r square, a quadratic in r and an exponential minus zr by 3a0. The quadratic has two roots. Both of them are positive. Okay. Let me write somewhat legibly, two roots. Okay. Both of them are positive, and the roots are such that you can write this as R3 1 r as r minus the first root a1 or minus a2 the second root multiplied by e to the minus zr by 3a0 such that a1 is less than a2. Okay. Now this is fairly clear how it should look like when we plot them. For all values of r less than the smallest of the two, this is negative, the product of the two negatives, therefore it is positive, and this function of course is always positive for all values of r which is from 0 to infinity here. So the graph is positive from 0 to a1. Between a1 and a2, you see this part is positive. Between a1, when r is between a1 and a2, r is greater than that, this is positive, this is negative, and this is always unchanging in sign. So what you have is at a1 there is a 0, the function goes from positive to negative between a1 and a2. And for r greater than a2, the function is again positive, but at a2 again it goes to 0. So there are two roots or two nodal points, 2 nodes A1 and A2. Sorry, let me go back to the previous graph. A1 and A2, these are the 2 constants, the 2 roots of that quadratic equation that you have here, and for this the function is 0, but the radial function is positive, negative, and then it goes to 0 because the exponential becomes dominant and it kills everything else. No matter what the increase is, the exponential decrease kills any power, any finite power to n. So the radial function that you have has 2 nodes and alternates. For n equal to 3, L equal to 0. Let me just do the 2 other cases quickly and then conclude the lecture. For n equal to 3, L equal to 1, it is easy from the functional form r into 1 minus zr by 6a0 times e to the minus zr by 3a0, that this has only one root and it starts from 0. Therefore you see that 0 reaches a maximum, goes to 0 at when this part 1 minus zr by 6a0 is 0, and then it becomes negative, it goes to 0 for very large values. The last for n equal to 3, L equal to 2, you see it is simply r square e to the minus zr by 3a0. It never goes to 0 for any values other than 0 and infinity, so it is a simple node. Okay. Now let us keep these things in mind. Again the question will come in that for some values of r, the radial function starts from r equal to 0. R equal to 0 means what? It is the nucleus. Does that mean that the electron is there in the nucleus, in the region where the nucleus is? R equal to 0, sometimes the function is 0. So I mean, what do these things mean? Again the same answer, the wave functions themselves do not have any interpretation. When we take the absolute square of the wave functions, all these conceptual difficulties we have with the wave functions will disappear, and we will continue this in the next lecture where we will complete all these basic ideas about the wave functions as well as do some numerical calculations on what is called the electron probabilities, the electron distances, the average distances, the distances of where the electron probability is maximum, and so on. Until then, thank you very much.